Before watching this video, you should know that this is actually a segment of a larger video series called the Ultimate Linear Algebra Guide, where I cover each concept more in depth with larger videos and have problems and solutions attached to each video that you can work through. The resource is completely free, but the videos themselves are a little bit longer, so it takes me a while to make. Go ahead and check the description if the linear algebra guide video for this corresponding concept has already been released. And if it has, go ahead and check it out because it is the better resource. Otherwise, until it does, you can stick around and watch this video. Make sure you subscribe and turn notifications on so you'll know when I do release the corresponding Ultimate Linear Algebra Guide. And with that, we can get into the video.
Okay, so we've already worked with matrices in row echelon form, sometimes abbreviated as REF, but there's another form that we can keep a matrix in that will more often work with in the future, because it makes the solutions a lot easier to see by just inspecting the matrix. We call this reduced row echelon form, or RREF. Now, essentially, reduced row echelon form, as the name suggests, is just row echelon form, but reduced further. So let me show you what I mean by that. Let's look at row echelon form that we're already familiar with first. So here, this is a form of a matrix where we created as many leading ones as possible. So we have a leading one here and a leading one here. Now, this isn't a leading one because it's not the first non-zero term in its row. Whereas these are the first non-zero terms in this row, in their rows. But we can in fact take this a step further, and instead of just making them the first non-zero terms in their row, we can make them the only non-zero terms in their column. And that's the main difference between row echelon form and reduced row echelon form. The way you identify whether a matrix is in REF or RREF is you check their column, you check the leading one's column and see if it's the only non-zero term in that column. So let me show you what I mean by that. Basically, if you look at this column over here, well, we see that this leading one is the only non-zero term in its column, but this leading one isn't. Why? Well, there's a 2 here, and this 2 is a non-zero term in this column. So since there is a non-zero term in this leading one's column, this matrix cannot be in reduced row echelon form, but it's in row echelon form. Now let's move on to this matrix over here. Here we go down the leading one's column and we see if there are any non-zero terms in their columns. Well, this leading one's column, there are no non-zero terms, and this leading one column, there are no non-zero terms. So this must be in reduced row echelon form. Basically, all we have to do to check the difference is go down all of the leading one's columns and see if there are any non-zero terms in those columns. Okay, let's also go ahead and try describing the solution to this to these systems of equations. So previously I used the variables x, y, and z, but as you can see there are more than 3 variables here. So instead of x, y, and z, I'm going to use x1, x2, x3, and x4, and that's the convention we're really going to go with in the future. So you should already be familiar with describing the solutions using row echelon form, and these two are the exact same matrices, just in different forms. So what I want you to do is I want you to pause the video and try describing the solutions in row echelon form, and come back and see that you'll get the same thing using reduced row echelon form. Okay, cool. So let's go ahead and write out the solutions using the reduced row echelon form matrix. So here we will have let's work from bottom up as we usually do. So x2 plus x3 plus x4 is equal to 0. Now, the first thing that you should realize is this isn't a system that has one solution. This is a system that has infinite solutions. And why can we realize that? Well, firstly, the most important point is there are 2 variables here that don't have leading ones in their columns. That's x3 and x4. If you go down this column, x3 doesn't have a leading one. Like I said earlier, this isn't a leading one. And if we go down x4's column, x4 doesn't have a leading one. So since we have 2 variables without a leading one, x3 and x4 are both free variables. So we've already worked with the scenario where there's one free variable, but now we have a scenario where there's two free variables. So let's go ahead and see what we do here. Well, we have to set x3 and x4 equal to something. So let's set x3 equal to t, where once again, let me do a better job at that. X3 is equal to t, where once again t is just some real number, and let's x4 equal s, where s is some real number. And these are usually the variables we use as free variables when there's two of them, t and s. So if x3 is t and x4 is s, where both of these are real numbers, we can take those and substitute them into this equation and solve for x2. So let's do that. Let us go ahead and take x3 and x4 and substitute it in for t and s in these equations. 1 second. Okay, so like I said, x3 is t and x4 is s. Now here we're supposed to give the solution to x2, so we can go ahead and do that and show that x2 is equal to minus t minus s. And that's perfectly fine because we have two free variables here and our solutions can be in terms of free variables. In fact, they have to. There's no other way we can describe the solution. So let's do that for the first equation as well. x1 plus 3x3, which is just t, so 3t, plus 4x4, which is just s, so plus 4s is equal to 5. Now, if we can go ahead and solve for x1, and that gets us x1 is equal to 5 minus 3t minus 4s. And these are the solutions to our system of equations. And this system, since there's free variables, this system of equations has infinite solutions. Remember, a system has infinite solutions when there are free variables, and there's free variables when columns of variables don't have a leading one, like in this example right here. Okay, so let's move on to try and converting a system to reduced row echelon form. Because we learned how to interpret it, now all we have to learn how to do is make a matrix into that form. So let's use this example to do that right here. Now, converting a matrix to reduced row echelon form is very similar to converting a matrix to row echelon form. The only difference is instead of just making leading ones and eliminating any non-zero terms before it, we need to eliminate any non-zero terms in the columns as well, which is kind of intuitive, but from like the definition. But it's still worthwhile working through an example on how to do it, even if you're a little bit confused right now. So let's do that. So this matrix is 1 and then y is 0 because it's plus 0 y minus 1. And the last column, which is just added on of what all of these equations are equal to, just represents this 0 here. 3, 1, 0, 1. Minus 1, 1, 1, and 4. So this matrix represents this system of equations. Okay, so just like in our previous example, the first step is creating our first leading one, which is already done for us. But now, instead of moving on to creating our second leading one, we'll first go ahead and eliminate any non-zero terms in this leading ones column. So we need to eliminate this term, and we need to eliminate this term. So let's do that. To eliminate this term, it's very similar to when we eliminated any non-zero terms before the leading one. We look at the term, we go up the column, we try to find the leading one. So this is the leading one right here. So we need to use this leading one to eliminate 3. How to use a 1 to eliminate 3? Well, 3 minus 1 times 3 is 0, so we need to subtract 3 times row 1 from row 2. So let's do that. Row 2 minus 3 times row 1, and we want to substitute that in for row 2 because that's where we're trying to eliminate the term. So here we will get, well, the first row will remain the same because we're only affecting the second row of our matrix. We're adding on this column. So here 3 minus 3 is 0. 1 minus 0 is 1. 0, so 0 minus minus 3 is 3. And 1 minus 0 is 1. Okay? And the last column, the last row, sorry, remains the same because we're only affecting row 2 of our final matrix. Okay, now we've successfully eliminated the 3, now we have to eliminate the negative 1. So let's do that. Once again, we go up the column, we find the leading 1 in the column. This is the leading 1 in the column. We need to use a 1 to eliminate a minus 1. How do we do that? Well, minus 1 plus 1 is 0, so we add the 2 rows. So we need to add row 3 and row 1. So row 3 plus row 1, and we want to change row 3 in our final matrix because that's where we want to eliminate the minus 1. So how will that look like? Well, row 1 will remain the same because we're only affecting row 3. Row 2 will remain the same because we're only affecting row 3. Row 3 will change. Minus 1 plus 1 is 0. 1 plus 0 is 1. 1 minus 1 is 0. And 4 plus 0 is 4. Okay. So we've eliminated every entry in the column with this leading 1. Now we need to eliminate every entry in this column for this leading 1. So the first entry is already eliminated for us, which is nice. That won't always happen. But the second entry, or the last entry in this column, isn't eliminated for us. So we need to eliminate this 1. Also, we didn't have to divide this row to create this leading 1. That doesn't always happen. We will have to occasionally divide the row to create a leading 1, but here it worked out nicely. So we don't have to divide this row to create this leading 1. But we do still need to eliminate this 1 over here to put this matrix in reduced row echelon form. So let's do that. So to eliminate this number, we go up the column, we find the leading 1. This is the leading 1. So how do we use a 1 to eliminate a 1? Well, we subtract the 2 rows. So we subtract row 2 from row 3, and we change row 3, because that's where we're trying to eliminate the term. So row 3 minus row 2, and we want to eliminate the term in row 3, so we substitute it in for row 3. So the first row will remain the same, because we're only affecting the third row of our matrix. The second row will remain the same. And the third row will become, well, 0 minus 0 is 0. 1 minus 1 is 0, just like we wanted. 0 minus 3 is minus 3. And 4 minus 1 is 3. Okay, so we've successfully eliminated every row in this column. Now we need to create the last leading 1, which is using this minus 3 over here. So to do that, to create the last leading 1, we need to divide this entire row by minus 1/3 to make this a 1. And then once we do that, we eliminate every single non-zero entry in this column. So let's first create the leading 1. So minus 1/3 row 3, and we can then change row 3 because that's where we're making the leading 1. So 1, 0, minus 1, and 0 because we're only affecting the third row. 0, 1, 3, 1 because we're only affecting the third row. And here 0, 0, 1, and then 3 over minus 3 is minus 1. Okay, now we go ahead and we have to eliminate every other term in this column that's non-zero. So we need to eliminate this 3 to eliminate this minus 1. And then we've successfully converted our matrix to reduced row echelon form. So let's first eliminate the minus 1. We could eliminate either terms first, but I'm just doing the minus 1 because, yeah, you can choose your order, it doesn't matter. So we can eliminate the minus 1, and to do that, well, we go down the column, we find the leading 1. This is the leading 1 here. We somehow need to use a 1 to eliminate a minus 1. Well, minus 1 plus 1 is 0, so row 1 plus row 3 should do the trick. So row 1 plus row 3, and we want to change row 1 in our final matrix because that's where we're eliminating the term. So the first row will change because we're changing row 1. So 1 plus 0 is 0. 0 plus 0 is 0. Minus 1 plus 1, just like we wanted, is 0, and then 0 minus 1 is minus 1. So we've successfully eliminated the minus 1, and then row 2 and row 3 will remain the same. Now we only have to do one more operation to put this matrix into reduced row echelon form, and that's eliminate this 3 over here. So to eliminate the 3, we have to go down the column, see where's the leading one. It's right here. So we somehow need to use a 1 to eliminate a 3. Well, we can do 3 times row 3 minus row 2 minus 3 times row 3. So let's do that. So row 2 minus 3 times row 3 should eliminate this 3 over here. And we want to change row 2 because, well, that's the place we want to eliminate the term from. So 1, 0, 0, and then we add on the column, we keep a minus 1 here. So 0 minus 3 times 0 is 0. 1 minus 3 times 0 is 1. Now 3 minus 3 is 0, just like we wanted. And here we get 1 minus 3 times minus 1, which is 4, because that's 1 plus 3. So 4. And finally, the last row is 0, 0, 1, minus 1. Okay, so now I'll show you why reduced row echelon form is so convenient. Here, if this was row echelon form, we would have to work our way bottom up, write out equations, and substitute variables into other equations. Whereas here, by putting our matrix into row reduced echelon form, we've essentially already done that in the process. Here, we can just write x is equal to minus 1, y is equal to 4, and z is equal to minus 1. So through making a matrix into row reduced echelon form, we automatically obtain the solutions when we write out the equations. If this matrix was in row echelon form, we would have to take variables and substitute them into other equations to obtain the same solutions. I encourage you to just go back in this video and try solving this same system using row echelon form and seeing that you obtain the same solutions. But here, it's a lot more convenient because we just get the solutions automatically. When we put a matrix into row echelon form, we used a method called Gaussian elimination. Here we're using a method called Gauss-Jordan elimination. So we add on the Jordan part whenever we are putting a matrix into row reduced echelon form instead of just row echelon form. And yeah, this is the form that we're going to use for the majority of the course from now on. It might be more easy if you have to solve a matrix by hand to use Gaussian elimination, but here we use Gauss-Jordan elimination, and soon enough, you'll probably not even be needing to do this by hand. You'll be using a calculator, but it's crucial that you know the process, hence this entire unit.